Hey, good afternoon. Thanks for joining me for the last session. Feel free to follow along. If you go to that bit.ly, that'll link to the GitHub. The GitHub has a copy of the slides and the code that I'm doing later. So if you're that kind of person that likes to learn hands-on, please head out. So the bit.ly is deep-tex. So I work at Galvanize as an instructor. The stuff that I'm talking about today is actually part of two classes I teach. I teach an 8-week natural language processing class, and I teach an 8-week deep learning class. So that's 16 weeks of content that I'm going to not jam into an hour, but just kind of go over at a high level. Also, Galvanize kind of like supports a broader learning community. So we do a lot of events, informal learning places. We also host workshops, conferences, and we also have immersive programs if you're interested in kind of like longer term programs around data science and web development. Great, so like I said, I'm gonna kind of do a high level overview. I think I've taken all the math out of the slides. We'll see what we can do with that, so 20 minutes of that. I'm gonna then show kind of an extended demo that'll kind of like make this more concrete. I have a second demo that I'm have as a backup. I'm not committed to doing that demo. And then I'm very aware that the drinks are right after me. Cool, so let's start with the foundation. So the foundation is text. Text is what we use to communicate. It's how we read, speak, write. And so that's kind of really fundamental to the human experience. But more importantly, language also shapes the way that we plan, dream, and think. So it's this like very broad, ephemeral topic. And that's kind of what attracts me to it. It's this like mysterious thing that's inherently to almost all humans, and we try to understand it the best we can. However, the trick is that we have to digitize that. Since we're computer scientists, everything has to be digitized, and that's actually a big trick, is to take this like ephemeral like thing and digitize it. Like, how do you turn poetry into ones and zeros? How do you digitize this kind of thing? And that's kind of the big trick. And that's what we're going to talk about today, because humans like words and numbers like computers, and we just want to try to come up with clever ways of making the conversion from words to numbers. I also think it's like important as we move to the next generation of systems, which are being called artificial intelligence, that we realize that a lot of that's going to be text-based. So initially, we did a lot of things with images, and now increasingly with video. But ultimately, text will help us understand the human condition and help artificial intelligence kind of bridge that gap. Cool. But it's very, very hard. So the idea is that language has ambiguity. We have puns. We have colloquial terms. We have idiomatic. We have slang. It's constantly evolving. And so it's very hard to create these models and keep them up to date. But we'll do the best we can. And we also know from experience that building things with computers is hard. I was actually pretty impressed last night with the iNaturalist at the Lightning Talk, which actually solved that problem. You can use their app to take a picture of an object, of an animal, and it'll tell you that it's an animal. So we're coming along pretty well. So the saving grace is neural networks. So you just throw a neural network at it, and it solves all your problems. And so that's what we're going to try to do today. And onward we go. Another fun slide about deep learning. So there's a variety of approaches to deep learning. We are going to take the last approach. We are going to pip install something and call that library and call ourselves deep learners by the end. Cool. But no, in all seriousness, deep learning is amazing at finding patterns. And so if there's underlying structure in the data, deep learning is able to then generate a representation of that deep structure, give enough training examples and enough training time. So it's an amazing system that actually does work really well once you understand it. And one of the reasons why it's becoming increasingly popular over machine learning is that the more data you give deep learning, the better it gets. And there's a lot of text data in the world, and hopefully some of it's applicable to your problems, and then you can just keep training a deep learning system to get better and better over time, and it has that like, nice curve versus kind of traditional machine learning systems, and that's why kind of deep learning has taken the world by storm. So deep learning is often taught as a metaphor about the brain and using the brain as biological inspiration for this system. I don't think that's the best metaphor. The metaphor I like is just looking at it like graph theory. And if you think about it, it's a directed acyclical graph where we have a series of edges and nodes, and then information can flow from input through a series of other nodes to outputs. And so our job is to define the inputs, and then ultimately the model learns the rest of the features for you. And so that's what we're going to talk about today, is like kind of defining the edges and the nodes and understand that. Okay, I'm going to take a quick pause there. Any questions so far? Okay, let's move on. So this is the most technical slide here. So what we can do is we can look at a single node in there, and what we can think about as a single node is it connected to other nodes. And so it receives input. And so it receives a series of signals from other nodes. And then what it does is it just aggregates them. It creates a weighted sum. So it takes each of those items and multiplies it by some weight, usually called W. And then it sums them up. And then it passes it through a nonlinearity. And so what that nonlinearity is that small numbers will remain small, and then big numbers will get really, really big. Instead of a linearity, which just means that as numbers increase, the output also increases. And that nonlinearity is at the heart of deep learning systems. That allows deep learning systems to learn complex patterns because it's able to then weight things appropriately. And then it sums up all those packages and then pipes it to the next node. And so what will happen is that that one input at one layer will sum up all the information it has, pass it through some nonlinearity, and then that becomes then the input to the next layer. And we kind of just keep repeating this all the way through the whole chain. And then a nice working definition of deep learning is just one that has more than one hidden layer. And this is kind of like the big breakthrough through the field, was actually how to learn how these systems learn. And so actually training a model that is deep like this, that has multiple hidden layers, is incredibly hard because you don't know how to assign credit to different units that are active. So if one part of the system's active and contributes, how do you make sure you allot credit to that? Ultimately, we found a way to do that that's really great, well beyond the scope of that. It's called backpropagation, or backprop. And what backprop does is take the difference between the output and what you expected, and then moves it back through that chain. Cool. So we're going to focus on a very specific problem because it's relatively straightforward. It's classification. So what classification is just discrete value prediction. So we have different groups, and we're going to put different items in different groups. So you might remember this from elementary school or the iNaturalist talk from yesterday. So you have a group of invertebrates, and then you can have a group of vertebrates, and then you can kind of move down to different kinds of invertebrates. And an individual example only belongs into one of those groups. And so that's why our goal is to see an example and then put it into one of those groups. With text classification, we can do the same thing. So in this case, what we see is we have groups of words, and we can put those groups of words into categories. The most common example is your email spam filter. So some of your email, based on the groups of words, goes into your inbox. Based on another group of words, it goes into your spam filter. And that's what we're going to do right here. And so the goal of the deep learning system is to learn which words are a signal for spam, and then which words are a signal for not spam, or sometimes called ham. And so that's kind of what this is saying right here. The input is going to be just the words of a document. And we're going to take the words of the document, and we're going to weight them and see how important they are for classifying that in this example. And then we're going to have an output. And we're going to start very, very simple and have a binary output. So we're going to belong to one group or another group. Cool. Any questions before I move into the demo? Yeah. So there's a variety of nonlinearities. I should have just put nonlinearities instead of a sigmoid function. So the idea behind a sigmoid function is that that if the input is very, very small, it's bounded at a certain value, and it's very, very big, it's bounded at another value. And then values in the middle are free to vary, but there's a bound at the edges. So if like the input is very, very small, it just doesn't go to negative infinity, or if it's very large, it doesn't go to positive infinity. So those bounds constrain it. So as you push it in, it gets squashed. Things are bounded between two groups, but ultimately that value is actually, it's the output of a sigmoid actually is another real valued. So if you go on the y-axis, it actually is a continuous valued value. So we haven't quite gotten to the two groups yet. It depends on that, yeah. But that's yeah. Mm-hmm. So the question is, what are the kind of terminal or leaf nodes? So there's two sets. The one on this diagram on the left-hand side is the input. So for us, that's the individual words. So we're going to say, hey, we see this word, and we're going to get some activation for that word. It's going to then cascade through the network, and ultimately it's going to have an output. The output's going to be a prediction. So you'll see the kind of prediction here. So it's going to predict whether it belongs to one group or another group. Cool, and then back here. Yeah. Mm-hmm. We'll get there. So the question is about some of the details of the current neural net, and you'll see that in the demo. Yeah. Yeah, so the question is, how does training work? The training works because there's going to be, you're going to see a group of texts, and you're going to have an associated label with that. And that label is either going to be correct or incorrect. And then if it's correct, we're going to say, yeah, good job, network. Just stay the way you are. If it's incorrect, it's going to then take and adjust the weights to try to make it more correct on the next try. And then it's going to see this again and say correct or incorrect. If it's incorrect, it'll then adjust the weights. So it's just a matter of seeing the data over and over again, but it's based on having labeled data. In this case, labeled data is also called supervised machine learning. Mm-hmm. So the question is about kind of the mechanics of like, oh, you have like language can be short or language can be long. So how do we handle that? And then what is the actual structure of that? It'll all be revealed in the demo. Cool. With that, we'll try to jump ship to the demo. Okay. Okay. So what we're going to do is we're going to train a neural network to predict the likability of movies based on text reviews. So this is your classic thumbs up or thumbs down for a review. So that the input is the actual movie review. So they're text reviews. If you look at IMDb or Rotten Tomatoes, you'll see people watch movies and make a review of them. And then ultimately we can group movies into good movies and bad movies. And that's kind of how we're going to think about that. Okay. Whoops. Oh, real quick. So I'm in a Jupyter notebook. So a Jupyter notebook is a nice way to mix code and images all together. So that's kind of what we're doing right here. But ultimately, this is backed by a Python kernel. So what I'm going to do is I'm just going to reset my namespace to make sure that there's nothing hanging around there I don't want. And then just to kind of show you what is going on under the hood, here's the config file for this environment that I set up. So a couple highlights. We're using Python 3.6, so there's some nice features that we're going to use in Python 3.6. Like I said, we're going to use Jupyter Notebook. Rise is a package if I wanted to convert these to slides. So it's a nice package there. And then the two deep learning packages we're going to use, one is TensorFlow. TensorFlow is a great open source project from Google. So we're going to use TensorFlow 1.0. And then there's another great package called Keras. We're going to use version 2.0. What Keras does is it wraps TensorFlow. And so you can think about TensorFlow as like the C programming language that has great deep learning primitives, but it's a little hard to use and it's a little hard to get up to speed. Whereas Keras is a lot like Python, where it's a lot easier to read and easier to write. So we're going to write some Keras code, but ultimately we're going to then delegate it to TensorFlow to do the work. So TensorFlow has data sets already built in. So we're going to use one of the built-in data sets. This data set is from the International Movie Database, imdb.com. So here it is. And then what it is a data set of 25,000 movies, and they're labeled by sentiment. Sentiment just basically means positive or negative. You can think this as binary, 0 or 1. So here's a movie review. I wish I had more hands because I would have more thumbs. And because of this, movie is so terrible because then I could give it so many thumbs down that thumbs down would no longer mean anything because this movie is so terrible because it sucks so badly. Any idea if this is a positive or negative review? So this is an example of a negative review. Yep. Okay, and then we have another one. Lorenzo Lamas is awesome here. While he isn't required to act, he is quite fun to watch and a really cool character. Has a lot of charisma. However, even he can't save this one. He has no chemistry with the cast either. He rules. It's a little trickier, yeah, but we can consider it negative even though it has other things. So it's not necessarily straightforward on what's going on with these reviews, but hopefully our deep learning network will help us pick it up. Okay, so I'm gonna load up the data. So what I did was, even though there's 25,000 different reviews, I decided to limit the number of words in each review to 1,000 words. And that just keeps it easy. I'm actually going to fit this on my laptop. If you're doing this, you probably want to beef your machine. Possibly some graphical processing units, GPUs are very good for this. But given the fact that it's just a demo, we're just going to use, we're going to limit it to 1,000 words. And then there's another thing that I'm going to up there, which is skip top 25. So oftentimes in language, we have a lot of common words. The, and, I'm, they don't really mean anything, and they definitely don't contribute to the sentiment of a topic. Those are often, unfortunately, called stop words. So we're going to remove what is technically called stop words, just the most common words, because they're probably not going to contribute. Okay. So what happens is a lot of the heavy lifting for us has already been done for the data processing. Each of the reviews has been encoded as a sequence of integers. So we have to digitize these words. And in this case, we're just going to digitize them by how common they are. So if we see an integer, and we'll think about it as a, so if we see like the most common word is probably like I, and the second most common word is the, we'll just start seeing 1s and 2s instead. So that way we kind of very quickly move away from heavy strings, which are very hard for processing, into kind of lighter weight integers. So we'll end up with each review as a list of integers, which will help for the encoding. Okay. So again, the goal is to take all those words and determine whether the sentiment is positive or negative. Yeah. Mm-hmm. Mm-hmm. Yep. So yeah, if the review is like this is a great movie. So if the review is just 4 words, then what we're going to do is we're going to encode each of those as a single integer. Say this is in the top, is number 51. This is probably another common word. Maybe it's 20. Is 10. And then A is, even more common, 2 or 3. And then movie, probably relatively common, maybe 100. And so then that way we kind of take all of those texts and encode it as a list. And so we're going to end up with just 2 categories. We're going to end up with positive category and negative category. Yep. No. So we are still dealing with a relatively dense vector. So it's a vector because each review is like that. And so then we can put them all together, and we'll put them all together. But each row will be a movie review, and then each column will be the first word in the column, first, second word, third word, like that in the review. So we're still maintaining the integrity of the reviews for now. So here's another trick we're going to do, and this kind of goes to someone's question about this, about how to deal with reviews that are long and reviews that are short. What we're going to do right here is we're actually going to take and we're going to truncate them to 500 words. So then that way we just limit the reviews from that. And so either reviews are going to get cut off at 500 words, or they're going to be padded with zeros just to represent the fact that they're just short. So everything's going to be the same. Once we do this, we're then able to take all these independent vectors and put them into a same matrix, because the matrix has to retain the same size. And so we need some way to convert all these different length vectors into the same matrix. And then this is where we get the matrix. And the first one is the rows, which is the number of reviews. And then the columns is the second number, which is the number of words. Yeah. Mm-hmm. You are correct. So the question is, hey, reviews oftentimes will be, kind of telling a story, and they'll get to a punchline at the end of the review. Aren't we losing that information? Yes. We're actually losing a lot of information right now, and the reason why is just because it's kind of a demo, and so we're just going to kind of do a lot of shortcuts to get to the end. But if you were actually doing this to kind of do the best job possible, then we would want to include as much information as possible, and we're losing a lot of information, including possible things that are happening at the end of the review. Okay, so now we're going to define a model in Keras. So what we can do is go from the Keras package, import kind of the raw elements that we need. And then this is a loose architectural diagram of what we're going to do. And so what we're going to do is we're going to weight each of the words as they come in. And then we're going to learn the coefficients for that. And then we're going to use a series of nonlinearities to then either amplify the importance of a word or attenuate the importance of a word. And then we're going to pass it through a series of those to ultimately lead to a prediction of a class, either positive sentiment or negative of a sentiment. So this is what it looks like to build a model in Keras. So the first thing we're going to do is we're going to define a model. And so a model will be an instance. In this case, it's an instance of a sequential class. The sequential class just basically means that we're going to do one layer, we're going to do another layer, and we're going to do another layer. And so we're just going to have a series of layers. There's other more exotic architectures that we're not going to cover. And then to that layer, what we're going to do is we're going to add an embedding layer. And so this embedding layer is kind of a fun trick. So what we have is we have each word, or sorry, each review as a vector. We're going to take that vector, and then we're going to take that individual vector and project it into a matrix space. And then we're going to learn the weights of that matrix space. So if you were at Rachel Thomason's talk earlier, she talked about that. There's another type of embedding called word to vec. So this is not word2vec, but it's a variation of word2vec, but it's a common way of doing things because what we ultimately want to do is start clustering the words in that space. So instead of having a vector that just has the words in the order in which they appear in the review, we're going to project it into a second space, and that second space is going to cluster based on meaning. And so that's what this embedding trick does, is project our linear vector into this other dimensional space, and we're going to learn some kind of mapping from that vector to that space. But now that we have a matrix now, we need to take and make that matrix back to a vector to feed it back into the next layer of the neural network, and that's what flatten does. So what flatten does is take that embedding space and kind of concatenate it into a vector. And then once we have that, we're going to then apply our nonlinearity. Previously, I showed a sigmoid nonlinearity, which ends up, bounding values. There's another nonlinearity, which actually is a little more powerful. It's called ReLU, for rectified linear unit. The details aren't important, but it's just a nonlinearity that just happens to work a little better than a sigmoid. And then we're going to do another quick trick. This other quick trick is called dropout. Turns out that neural networks are too powerful, and they actually overfit the data. So what we're going to do is we're going to take and prune or cut some connections randomly, and then we're going to prune those connections, and then that neural network doesn't overlearn for that particular data item, but and then is able to learn a variety of data items. And so that's kind of another trick that we can do right here. There was a question? No, so doc2vec is a particular type of embedding. We're doing a kind of a generic embedding, and yeah, that's kind of the short answer. Mm-hmm. The top graphic is a pretty loose architectural diagram of what we're doing. It's not exact. What we're doing is we're taking a vector of inputs. Go ahead. The top part right here is these input values ultimately get weights on them, and so then there's embedding weights from the input review into the embedding space. So there's a set of weights there. Yes, it is. That's the first set of weights that we're going to learn, is the weights that's going to embed the vector into our embedding space. So that's the first set we're going to learn. Mm-hmm. Yep. Yes. It's 32 dimensions. So what we're going to do is we're going to take our vector of inputs, which is going to be 500 long, and each of those is going to have an input representing the frequency of the word, and we're going to take that input vector and we're going to project it into a 32-dimensional space. Yes, it's dimensionality reduction, but as we're doing the dimensionality reduction, we're hopefully capturing some of the important features of the words about which ones are important for our task. Yeah. Mm-hmm. So the question is what's the relationship between this and bag of words? So bag of words is another machine learning technique. What bag of words says is that the word frequency occurring is more important than the actual sequence information about when words actually occur. So what we're going to do is take the equivalent of taking text, chopping it up, and putting it in a bag and shaking the bag, and then pulling the text out. And that's going to give us information about how often words occur, but not when they occur. This is related to that. So I wouldn't necessarily say it's a direct bag of words model, but it's related in the sense that we're actually not modeling the sequence information directly. No, we're not doing any of that. Yeah. Yeah. Mm-hmm. So I'll show you that. That's a question is like, when does the dropout happen and how does that work? Hold that thought until we walk to the end and then it'll be more clear. So here's our dropout. And so what we end up having is, then we end up having what's called a dense layer. Dense in Kera speak just means fully interconnected. So we're gonna fully interconnect our flattened matrix to this output layer. And so then we'll have this other next fully interconnected layer. And then ultimately, we have a series of activations of our network. So we see a series of words. Those words get weighted. That ultimately activates our network. We need to convert our network to a discrete prediction. We need to predict positive or predict negative. The way to do that is now to use another nonlinearity. In this case, we're going to use the sigmoid, because a sigmoid we can ultimately convert to probability of class membership. So we can say, hey, if the sigmoid activation is low, we can say that's probability of one class. If the sigmoid activation is high, we can say then that's the probability of the other class. And so this sigmoid at the end helps us convert neural network activation into probability of membership for positive or negative sentiment in the review. So right there, I just built the model. And then there's a nice Keras helper function called model summary. And so what this does is this then tells us what's going on with our model. And it's kind of showing us the total number of parameters. So this model has 48,001 parameters. Most of the parameters are in that first embedding layer where we're mapping the words in the review to some kind of dimensional space. And then we're going to take that dimensional space and then we're going to map that to another neural network layer. That's ultimately, and then we're going to take the activations of that neural network layer and interpret those as class membership. Okay, so now this is the interesting part of Keras. So we actually are now leaving the dynamic land, and we're actually going to compile our model. So we're going to take and create a compiled version of our model. And the parameters that we're interested in here are these three parameters, which ultimately define how our model is going to learn. So the up ahead was our model structure. So that tells us the kind of the underlying architecture of what's going on, but we need to then tell the model as it's training how we're doing that. And these are kind of the most important metrics. The first one is loss. So loss tells us how wrong we are on things. And in this case, we have two groups. So we're going to use binary, and then we're going to use a version of that called cross entropy, which is built on information theory, which tells us how, some measure of the entropy of us being wrong. And then what we need to do is we need to search the parameter space for different kinds of weights. And there's lots of ways of searching the space. We usually use variations of gradient descent. Gradient descent is kind of a way to see the change in weights and kind of look for a local or global minimum. There's kind of a newer version of that called Atom. What Atom does is say if we're going downhill, go downhill faster. If we happen to change directions, slow down. So it's adaptive, and that's what the Atom part is for adaptive learning rate. And then ultimately we need to measure our success. In this case, we're going to use accuracy. The data scientists in the crowd might realize that that's not the best metric, but it's an easy metric to understand. So I've just compiled the model. And so now what I can do then is I can actually fit the model. And so in this case, I'm going to fit the model. And what I'm going to do is I'm going to do 5 passes through the data. Each pass is called an epoch. So we're going to do an epoch through the data. And then we're going to see kind of how we do on that. So a couple things. One is Thanks for bearing with me. But this is actually as fast as I could get through to actually building a deep learning model. If you actually checked in with the deep learning community a couple of years ago, it wouldn't have been this straightforward. And it would have been crazy to attempt a deep learning introduction in an hour. But given the kind of like Kera's package is actually relatively straightforward to define a neural network. Also, it's pretty amazing that we're actually able to train that on just a laptop. And so we can see right away that we're starting to increase our accuracy right here. So our accuracy is around 81%. So baseline's 50-50. So if we were just doing random guessing, we'd be at 0.5. We're well above that. Even within 5 passes through the training set, we're up to 85%. And so part of that has to do with the fact that even though I truncated the data and kind of manipulated some of the data, I was actually able to use some nice algorithmic tricks from the deep learning community to like do really well on a limited training set with a limited number of training epochs. It kind of shows the state of deep learning right now. So what I did was I withheld part of the data set to test. So what I did was I took some of the data set to train my model and to adjust the weights, but ultimately I had a holdout or validation set to make sure like I was actually not fitting to the exact text that I was seeing, but I kind of made a model that was able to like look at other texts, which in machine learning is called generalization. So I was able to then see how good I can do on the generalization. And the big reveal. So I'm able to get about 85.6% on the holdout set. So that's pretty good. Yeah. Mm-hmm. Okay, yeah. Mm-hmm. Yeah, so the question is about what's the relationship between the training and the validation. And during training, we review, we pass it through all the layers, we get an answer. We see if the answer is correct or not. If it's correct, we're like, good. If it's incorrect, we'll take and we'll update all the weights to make it more correct. But then ultimately, we have to move to what's called the predict stage. At the predict stage, we're going to hold the weights constant and see if we're able to predict on data we haven't seen before. Because during training, we actually made 5 passes through the data. So we gave the network 5 chances to learn this data. But it might have overlearned the data or might have learned something not quite right. And we want to make sure that our model is robust and able to like work in other contexts. And that's why we show it data it hasn't seen before, and we don't let it adjust or learn to that new data. Mm-hmm. Mm-hmm. Yep. Yep. Mm-hmm. Okay. So what happens is after we get the movie review and we then convert the words into integers based on their frequency, we then map that vector into a matrix space, because then it's able to then kind of cluster the words that are useful together in that matrix space. It's you're learning how the words are associated for these reviews. Mm-hmm. No, the words, the wording, the ordering of the words don't matter. Yep. Mm-hmm. Yep. Yep. Yep, that's right. We're going to have a large dimensional space. Just real quick, and then we'll move on. You will have a large dimensional space. We can see right there, we can see that space is actually pretty large because we're going to project each of the 500-word vectors into that 32 dimensions. And we can multiply those to see how many parameters that we're then going to learn, because we're going to learn all of those weights. And then that layer is going to be then fully interconnected to our dense layer, which is going to be another set of weights that we need to learn. And then ultimately, we're going to take those activations at that last layer and then kind of constrain the activations to be the sigmoid function to ultimately make a binary prediction. So we're going to take that kind of vector, put it in that matrix space, learn the weights, and then have a connection to another set of nodes, learn those connections, and then look at those activations. What ends up happening is that as we go through this training, it might overlearn the words. And so that's where the dropout comes into play, is that we're just going to randomly remove some of the connections, and it's going to have to like adapt to those removed connections. And so every time we go through the training, we're going to randomly remove those connections to then hopefully learn a more robust representation. So it's during the model training that it randomly removes those connections, and that's what that dropout function does. So does that answer your question? It happens throughout training. So what happens with the Keras model is that you create the model we did there, we compile it, and then we send it to TensorFlow. TensorFlow actually does the execution of that. So it's a little bit of a different model than the Python model. Yeah. It ignores it. So the Keras package realizes that I'm at a predict stage, and there's going to be no training at the predict stage, and so it'll use all the model weights at the predict stage. Mm-hmm. Yeah. We are 100% missing sequence, and yeah. Mm-hmm. Yep. Hmm? Yes, that's correct. So we are ignoring sequence, and the reason why is because I just wanted to cover the kind of the first neural network you would see, and how we can use the first neural network you would see to like do very good on this task. We actually, even though we ignored the end, we ignored sequence, we ignored a lot of information, we actually did remarkably well on this data set, and I'll actually show how well we did compared to the original work on this data set. We did an amazing job. Later on, as you learn more deep learning systems, you can learn sequence information. The most common kind is called RNN, or recurrent neural net. That actually then looks at the sequence information, and then as you go through the sequence, you then learn which sequences predict which groups. But that's definitely important. Okay. Yep. The backpropagation happens throughout the whole neural network. So as you go through the neural network, at every time you receive a scored labeled example, you then find whether that's correct or not, and then it backprops through the answer. So I'm going to say that that's the answer right now. There's kind of variations of backprop. There's complete backprop and stochastic mini-batch backprop, kind of beyond this. But that, I'm just kind of a high-level definition of that, but there's variations of backprop that allow you to do it more efficiently. Okay. The question is, how do we build these models? Like I gave this model right here that has these kind of nodes and edges. How do we know that? And it's at this point, it's actually just kind of trial and error. So there's kind of commonly published models, and you can copy the commonly published models or be inspired by them. But then ultimately, it's a matter of just tinkering with the model to see whether it increases or decreases that. That's kind of the state of things right now. So I'm going to kind of finish up, and then I'll take some more questions at the end. Okay, so here it is. one of my favorite XKCDs. So this is all linear algebra. So if you really want to understand deep learning, learn some linear algebra. And if we don't like the answers, we just start turning the pile. The interesting thing was that this data set was initially released in 2011, well before kind of deep learning took place. And they used kind of a collection of standard machine learning techniques. And their accuracy was close to 89% on this. So it's interesting that that's the state of the art for research papers in just 2011. And then we're able to kind of build kind of a toy demo model that's actually able to get relatively close to that performance. Okay, so I'm going to skip the second demo just for the sake of time. And then, so just a summary. I want to just say that text data is everywhere. So it's important that our models are able to model that. Deep learning likes that lots of data. That's one of the kind of the prerequisites of deep learning is to have lots of data. And so we have then the ability to kind of make sense of that. So we can actually train computers to then interpret these things, these human emotions and these human creations. And then Keras is a very approachable way to build deep learning systems. So we can focus on this kind of high-level understanding of the deep learning system without worrying too much about the mechanics. But once you get more into it, you'll want to start understanding the mechanics, and that's where TensorFlow comes in. TensorFlow allows us to work through the mechanics at a deeper level. Again, just a 1 hour kind of whirlwind talk. And then hopefully I've inspired you to kind of continue further study. One thing I can highly recommend is Jeremy Howard and Rachel Thomas's Fast AI courses. They're really amazing. They put all their videos, all of their notebooks on the internet. So they have an introduction course to deep learning, and they also have a more kind of applied deep learning course. Just this week, Andrew Ng, who released the seminal machine learning course, just released his deep learning course on Coursera. So I would just kind of check that out. That's really going to be coming forward the industry standard about understanding these deep learning systems. And then for me, I learn a little bit better from books. So this book is really amazing. And so I would just check out this book. It's really approachable. In addition, it actually covers a lot of machine learning foundations. So if you're actually new to machine learning, you can pick up a lot of the basics in that book also. And then one thing, if you're like me and really into text and deep learning, Stanford has an amazing course on deep learning right there. They have all of their course notes, all of their videos, and all of their code on the web. So I would definitely check that out, which will have a much deeper understanding of this type of model and then also sequence models. Oh, and then one last thing. It's best to learn through doing. That's kind of why I showed this IMDb demo, is to give you some idea of like playing with it. The code's on my GitHub. It's really good to like play and understand and try these models. They'll break, but that's okay. In this case, this is actually a binary computer. So the person really wanted to understand how computers work, and so they actually built a computer out of physical binary gates. And so you get kind of a deeper understanding of what happens through building projects. Cool. I love XKCD, and yesterday's comic was about deep learning systems. I thought it was pretty amazing. Cool. Okay, let's do Q&A.
You know how sklearn has like grid search capabilities where it can search many parameters at one time?
Yep.
Is there something like that in Keras where it can check different models instead of just having to reconfigure it by hand every time?
So the question, oh, you already answered it. Not to my knowledge. I think there are packages that sit on top of Keras that do that, and there's packages that sit on top of TensorFlow for searching for parameters of the model. One thing you'll notice very quickly about this, it becomes really hard. So it's like, it's relatively, there's a few parameters for many machine learning models, but then that becomes exponential for deep learning models, and so that's when it ends up becoming very tricky to doing good parameter searching, and definitely grid searching wouldn't be necessarily a good way to approach parameter searching for deep learning just because of the sheer number of parameters. But it's like kind of, at this point, it's actually an open research question, but there are some packages that help you. Yeah.
Question about the dropout function. So I get the math, but what's the practical effect if you don't have that? Does it guess no 99% of the time, or you know what I mean? You have your answer at the end is yes, no, and you're trying to get 100% accurate on that. If you don't have the dropout function, what happens?
If you don't have the dropout function, the model overlearns the data because there's actually just a limited amount of data, so it just memorizes the data. So it says, I see this review and I see this collection of words, and I know it maps to this answer, and it just memorizes that mapping exactly. And if anything changes in that mapping, it then doesn't learn a new mapping. So if the like this is a great movie, it'll just memorize that.
Right.
And then if someone says like this is a great film, it'll get confused because it knows movie but doesn't know the word film. And so dropout prevents that kind of just straight memorization of the data because deep learning is very powerful at learning these patterns.
Awesome, thanks.
Okay. I'll go here. Oh, okay.
I have two questions.
Okay.
One, I'm trying to conceptualize it. Is it similar to like PLSA or LDA as far as conceptually?
I don't know what PSLA is, but do you mean by LADA, latent Dirichlet allocation?
Yes.
Latent Dirichlet allocation is a whole different class of machine learning models.
Right, but is it conceptually similar?
No.
All
so
right.
LDA is a graphical model that learns kind of like these probabilistic topics.
Right.
This is just an entire different branch of machine learning, so there's not really much there.
And one more question, as a quick one. Does Keras do cross-validation?
I think it does, yeah. I think so. Yeah.
So when you're going through, it's sort of set up your model and then execute it.
Yes.
Is there any way for us to go through and say, okay, at this point, can you go through each of our little graphs for steps and show us the intermediates on one run through so that we can make sure we comprehend?
Yeah. So the question is that this is a kind of a different modeling perspective or different programming perspective of defining a model, compile and run it. So it's very different than like the Python, which allows introspection. The question is not in Keras. Keras doesn't allow that kind of introspection. TensorFlow allows you to then introspect the weights. So as you run the model, you can stop the model and then say, show me the current weights. So you can see which words are weighted towards which direction. And so you're able to do that through TensorFlow. It's just not built into the Keras package, but you're able to do. Yeah. Mm-hmm.
You mentioned that the current state of the field is sort of trial and error on designing the architecture.
Yep.
I'm pretty new to this, so I don't have much intuition. Is it quick to develop the intuition, like, oh, I see these symptoms, so I need more hidden layers, or is it difficult and it may be something that if you could design something that like auto-develops the best architecture, is that being worked on?
It is working on. So if you have a lot of extra computers laying around, if you have a couple extra data centers hanging around, you can work on developing deep learning models that learn deep learning models. It's a field of deep learning called learning to learn. It's like only a couple people or a couple organizations have the extra data centers hanging around to do that. For us that don't have that kind of access to that infrastructure, it's more through this trial and error, and it develops over time. But also helps that if you go to forums, if you work on these kind of common problems, there's kind of a set of best practices. Really, the best practice is to take created architectures and already use them. So this demo is actually loosely based on the Keras demo, and so you can use that that architecture, or you can download pre-made architectures and then just tune your model with those pre-made architectures. That's kind of the first couple steps. And then from there, you can kind of like work on developing your own intuition.
Cool. Thank you.
Okay.
I wanted to ask about best practices. You mentioned accuracy isn't a good metric.
Yes.
I'm interested to know about ReLU versus sigmoid.
Okay.
And whether or not TD-IDF transformers are still in vogue.
Okay, there's 3 separate questions, and I'll hopefully knock them out. And if I forget. Okay, one is evaluation metrics. Accuracy just means how many did I get right out of the total amount. Accuracy works really well if you have balanced classes. So you have equal number of like one group and another group. In this case, I do, because I just have a little toy example. The real world doesn't have that. So you have uneven baselines. And so in the, there's oftentimes when you'll have 99% of your emails are good and only 1% are spam. You could get 99%, you can get 99% accuracy by classifying everything as good. But you're ignoring the problem, which is actually correctly classifying spam. So you want to use other kind of weighted metrics. So you can use precision, recall. There's another one that weights both of those called F1 scores. So it's just a question of what your problem is, defines on what your evaluation criteria is, and how you would transfer that into a metric. And so in this case, I could get away with accuracy because of like the example I constructed, but across the board, evaluation metrics really depend on the domain. I'm going to answer the TF-IDF question first and then talk about the other one. So TF-IDF is term frequency inverse document frequency. It's a kind of a text classification trick. And so what you're doing is you're going to say that this word is common in every document in my corpus. And so in this case, documents are the movie reviews and the corpus is all of them. So, like the word and might appear in all of those. So I want to downweight that. And then I want to say, like, if I say the word like I'm trying to think of like if I say like film noir might be like less common, it might be very important. And so that's a less common word. I'm going to upweight that word. What ends up happening here is that this system learns not the frequency of the words, but the importance of the words for this task. So it then learns to weight how important it is for this specific task, and doesn't need that pre-processing step. And that's kind of a bigger pattern in deep learning. Deep learning is end-to-end systems where you just give it the raw input and then you get a raw output and it learns everything in between, as opposed to having a person define each step in the pipeline. Actually try to minimize that just to show that it could do end-to-end learning, whereas the TF-IDF is just then you as a manual person defining a step in the process, whereas this should learn that through the connection of the weights. The last question is the choice of nonlinearity. There's a lot of nonlinearities out there. It just depends on, generally things in the rectified linear units are working a little bit better like right now, but then there's variations of ReLU, and then there's kind of variations of sigmoid. One's called TAN-H. And so it's just a matter of like it just depends on your domain and your problem set on which nonlinearity you use. The best is to learn a bunch of them and then pick the one that like works the best in that context.
Some say that ReLU has less computation intensive, given the resource. It's faster and lighter. Right?
Yeah, that's kind of the one. That's the kind of one general process. So for example, the sigmoid function, we showed that it takes in a real valued x function value, and it has a real valued y function that's bounded very tightly, but it requires a lot of compute since you need to calculate the y value for every single x. Rectified linear unit is flat and then linear. So if it's below a threshold, we just say it's 0. If it's above a threshold, we just take the y value. So it's much easier to compute. Also, you actually, when you do the backpropagation, it actually goes through the derivatives. And so then the derivative of a flat line is 0, and the derivative of a linear line is 1. So it ends up becoming a binary response. But that's a little more technical than I should have got. Okay.
So,
oh, yeah.
What would you do in order to increase the accuracy? I mean, you said you were close,
Yep.
but what would you need to do to get to that 2011, and then of course to get to 100%?
That's a great question. That's a great question to end on. So if I really wanted to make the accuracy better, what would I do? And so the accuracy is more data. So what I would do is I would not limit the reviews to just being kind of short reviews. I would use as much data as possible. Another one is compute. That's another big breakthrough in deep learning. So by compute means that I could run the data for longer. So I could use more CPU cycles. So I only train the data through 5 epochs. I could train it through 50 or 100 epochs. And then the last thing is algorithms. So I could actually define better algorithms. So I could use other variations of that. And so those are all the kind of big parameters that I could use to adjust that and get it up closer to that mark. I'll be hanging around to answer questions.
Thank you so much. One round of applause.